And it is my pleasure today to introduce our speaker, Alexander Weiß, with the talk Intermittency Phenomena for Mass Distribution on Stochastic Flows with Interaction. Please, Alexander.
Okay, thank you very much for the introduction. So I'm going to present to you partially work from my master's thesis, which was supervised by Andrei Anatolievich, and well, partially during my PhD studies, which was also a joint work with Andrei Anatolievich. Okay, so let me begin with the, okay, it doesn't work. Okay, so let me begin with the overview. First, I will do a little introduction, well, give a short recall, I hope, of what SDEs with interactions are. Then explain a bit about densities for mass distributions. And afterwards, I will already mathematically define what the intermittency phenomenon was or how we investigated it, and present the main result connected to this phenomenon, which we obtained. Okay, so as an introduction, I would like to say that the intermittency phenomenon has been intensively studied, for example, in the context of fluid dynamics, and here especially in turbulence theory, where its occurrence is connected to a chaotic system. And just for a brief description, Zildovich et al. In their paper described it as structures in which a growing quantity reaches record high values, and despite the rarity of these concentrations, dominates the integral characteristics. And what they meant by domination of integral characteristics can be described as follows. So let's assume we have some function indexed by time, which preserve mass. So let's just say their integral is equal to 1. And what the domination of integral characteristic means is that the pth moment dominates the qth moments for t going to infinity, or in other words, like this limit for t to infinity converges to infinity whenever p is greater than q. So when can these kind of phenomena happen? This can only happen when ft evolves into some spikes. So basically we need high values such that the function, well, x to the pth power, such that this function Hello? Hello?
Hello?
Yes, yes, we hear you.
Okay. Okay. I'm not sure. I was muted. Just I don't know what you've heard, but
No, you was just for a second.
Okay. All right. So I will just resume. Well, this can only happen when some spikes occur, because the integral has still to be 1, and well, since mass cannot be created, we have to concentrate at certain points to some peak. So the function x to the pth power contributes to this domination and outweighs the normalization by the pth root in the limit for t to infinity. And in this context, it is interesting to study such phenomena for densities of mass distributions for SDEs with interaction, because SDEs with interaction, for example, occur in evolution of stellar evolution of stellar mass, and yes, well, are used there. Okay. So I will quickly recall the SDEs with interaction. So first of all, we consider the pth Wasserstein space. Here I have written down the definition of its notion, and I guess it is well known to the audience that this is a complete separable metric space. Yes. And with such a distance function, where c mu nu is the marginals, or are the couplings with marginals mu and nu. Okay, so the main object of consideration was, as I already said, the SDEs with interaction. And in this context, sorry, the 0 shouldn't be here. We consider P in 1 to infinity and omega Fp as a complete probability space with infinite, well, countably infinite independent Brownian motions. And such coefficients functions such that they depend on space, time, and also on a measure. And for the diffusion coefficients, the same. And an initial measure, which is interpreted as the distribution of particles at the beginning, which is in MP, or in the Piet-Wasserstein space. Okay, then the following Cauchy problem is called stochastic differential equation with interaction for initial measure mu0, or in short SDE with interaction. And let me emphasize here that the main difference to normal SDEs is that the evolution of the process not only depends on the process, on the current state of the process, but also on the entire distribution, on the distribution of the process in space. So yeah, we start in U, which is conformal with the interpretation of like particles which evolve in time, and mu s, which is the main object of investigation, is the push forward measure of the flow under for fixed s. Okay, so as for every SDE, we need some existence results, and here in Andrei Anatolievich's work from 2007, there is an existence result, and for this existence result, we naturally assume like this Lipschitz condition, but not only with respect to the space, but also with respect to the measure. And for this reason, we use the Wasserstein distance. And we also want our coefficients to be at most of linear growth. Okay, I will do it with the mouse then. Okay, so now I come to densities for mass distributions and what we have actually investigated. And what we want to investigate is if the initial measure, mu0, is absolutely continuous with respect to the Lebesgue measure, then a natural question which occurs is mu t also absolutely continuous with respect to the Lebesgue measure? And if this Lebesgue density for mu t exists, or if the answer to the first question is positive, then what properties does this PT have? And especially we want to investigate moment properties. Yes, in more detail, the intermittency phenomenon, but I will come to that a little bit later. Okay, so the first step for existence of such a density for the mu t is the following. So consider a positive measurable function f, and let P0 be the Lebesgue density of mu0. Then consider such equation, the integral of f integrated with respect to mu t. Then by definition, this is the same as this integral here, where we inserted xut and decomposed the integral with respect to mu0 to the Lebesgue integral. And now, well, not a rigorous step, but if we somehow want to get rid of this xut in order to get a notion of a Lebesgue density, we would want to perform some change of variables, and very good change of variables, if possible, would be the change of variables u being equal to the inverse function with respect to u. And let's assume we could do that, then we would end up with this quantity, and then we would indeed see that mu t has a Lebesgue density, which is of this form. Okay, but here, some things come into play. So first of all, a derivative of the inverse and the inverse itself. And in order to make this computation rigorous, we need that the flow for fixed t is a diffeomorphism almost surely, but for all t uniformly. So the null set should be uniform for all t. But for this, we need further assumptions on the coefficients. So first of all, we need at least differentiability. And well, if we want differentiability of our solution to the SDE, our coefficients should also be differentiable. Okay, so in order to prove diffeomorphism property, we will assume the following. So let A and BK be continuously differentiable. And in the sense that they are continuously differentiable with respect to the spatial variable, but the coefficient functions themselves and their derivatives should still be continuous with respect to mu and with respect to t. Then we want the following conditions. We want that the partial derivatives are Lipschitz in this sense. And we also want that our derivatives are bounded like this. Okay, and why do we exactly want that? Because we want to apply the theory of Kunita on stochastic flows of diffeomorphisms. And in order to do so, we need to bring our SDE into a Kunita form, or into a form in the sense of Kunita. For this, we need, first, after obtaining a solution to our SDE with interaction with our existence result and uniqueness result, we want to fix the measure value process mu t, t being greater or equal to 0, and rewrite our coefficients in the following way. So AU mu t should just be AUT, but this is now a random coefficient. And the same we do with the BKs. Then we consider the semi-martingales in the following way. Vitali has done this in his talk in this seminar already, but I will quickly recall. We will rewrite it in this way. And then XUT solves this SDE, where it is an SDE in the sense of Kunita with such an, with such a kernel here. Okay, and well, now that we are in the context of Kunita, or in his notation, we can actually apply Kunita's theorem on the existence of a version which is a diffeomorphism, which more precisely is the following. So under the differentiability conditions and the uniqueness and existence conditions, there exists a version x tilde, which we will in the following also denote by x, of the solution to the SDE with interaction, such that almost surely for all t greater or equal to 0, this function here is a diffeomorphism. And moreover, we have this kind of formula for the derivatives, which is basically only the chain rule. Okay, application of the chain rule, better said. Okay. So now I will make an assumption for the rest of the talk. Firstly, it is due to convenience, but secondly, it is also due to the fact that the main result is only proven for such coefficient functions. And actually, there is only one step where we use it. And all the other steps would also work in a more general case, but I will emphasize further on that when time comes. Yes, so let for the rest of the talk, all the BKs for k greater or equal than 1 be 0, and we only consider B0 u mu t, which doesn't depend on t anymore. It should be equal to an integral kernel with some function beta, some interaction kernel, sorry, for some function beta, where beta is 3 times continuously differentiable, and the derivative of beta is a C2B function. Okay, and we will see that it will come in handy. Okay, and now to get a step closer to investigate the intermittency phenomenon, we need to investigate the properties, well, first of all, by the diffeomorphism result, by the same calculation as we had before. We now know that there exist Lebesgue densities, Pt for mu t, and we want to investigate these Lebesgue densities now, and especially investigate their moment properties. So in order to investigate the explosion of their moments, we need to show that if P0 is in LP, then also PT is in LP for all t greater or equal than 0 almost surely. So in order to to get this result, observe that for P greater or equal than 1, by a change of variables, we get that PTU to the power P is equal to P0 U to the power P times 1 over determinant of the derivative of XUT, and all this to the power P minus 1. So the regularity of PT in this case depends on the regularity of the determinant of the derivative. Because, well, if P0 is in LP, then we have no problem. For this reason, we will deduce the following analog to the Liouville formula, which is well known from ODE theory. And it looks as follows. So the determinant of the flow is of the following form. The determinant is equal to an exponential of the divergence of A with respect to the spatial variable of x, u, t, mu, t, t, and then minus a correction term, plus the stochastic integral of the divergence of beta x, u, t minus x, v, t integrated. Okay, this is a typo here. Sorry, this should be a v integrated with respect to mu0 and with respect to the variable v, and all this in a stochastic integral. And maybe a quick sketch of the proof. It is only an application of the E2 formula. So we can rewrite the SDE with interaction into Stratonovich form due to this concrete given form of beta, and then differentiate the solution to the SDE again, and then we get by...
Alexander,
yes.
Can I just interrupt you, because here it is a very good time to say that here the concrete form of the coefficient comes into play, because when in general setup we want to rewrite our SDE with interaction in Stratonovich form, we need to check that mu t itself is like semi-martingale or something, and it becomes to be a slightly technical work. Yes?
Yes, exactly. This is true, but it works here in a more general case, because one could rewrite there is a form in Kunita where you can rewrite the kernel of Kunito into Stratonovich form and then apply it again. So here it comes in very convenient to see the exact form, but I'm not entirely sure whether, well, it is useful here, but I'm not entirely sure whether it is needed 100%. I would want to investigate that a little bit further.
Okay. But as far as I remember, by the way, it was your note that here we need something from mu t in general. Yeah.
That was
okay.
Yes. That was back from my master's thesis. Yes.
Yeah.
Exactly.
Okay.
So,
let's go further.
But I think yeah. Okay. So yeah, as mentioned, so here it comes very in very useful, and we have such an explicit form. And by this explicit form, now we can show an LP property, and we can we can precisely show that if P0 is an LP for P greater or equal than 1, then this expectation here is finite. And from this, we can, get the result that the pth moments exists. And the sketch of the proof for this is the following. One can apply here again change of variables, then one can pull in the supremum. And since this thing here can be written as the solution of a linear SDE with bounded coefficients, then we can derive that the supremum of in U in RD of the expectation of this supremum here is finite. Yes, this is possible due to the concretely computed form. And with this at hand, we can now finally define the intermittency property properly and work with it. So let me define the notion of intermittency. For this, consider P0 to be in all of the LP spaces, or for simplicity, maybe in L1 and essentially bounded. Then the quantity gamma P, if existent, so if this limit here exists, gamma P is defined as the limit, if existent, of the natural logarithm of the integral of pt to the power p of u integrated with respect to the Lebesgue measure and divided by t. Then pt is called intermittent if the following here, gamma p over p for p greater or equal than 1 is strictly increasing. And why does it correspond to the intuition which I gave in the beginning of the talk? So if this is strictly increasing, this means that the pth moments grow faster than, the moments of the higher moments grow faster than lower moments. Because otherwise,
even exponentially
faster. Yes, it is even stronger than the notion that I mentioned, but one can deduce from this that the moments outgrow the higher moments outgrow the lower moments exponentially. Okay, so these are nothing but Lyapunov exponents for this special quantity, but I don't want to use that term here because it is reserved for a different quantity in the talk. Okay, so in order to investigate intermittency properly, we have to look what this integral.
Also, let me interrupt you. Can you just go to the previous slide?
Yes.
Because as far as I remember, maybe this is the Khasminsky moment Lyapunov exponent. Am I right?
It is, in a sense, it is. If you look at it abstractly, this is why I chose. I chose to define it like that. But in general, the Khasminsky-Lyapunov exponent is an expectation, and the expectation is an integral with respect to a probability measure. But here we just integrate with respect to the Lebesgue measure. So we have, in general, we have infinite volume, but we will actually reduce. We will only reduce our case to finite volumes because, in the main result, we only consider initial conditions with compact support. So it is.
So it is related.
It is related, yes.
Okay.
It is related, but it is not. The difference is what I said. We integrate with respect to infinite volume, which makes a massive difference in general. Okay. So yes, where did I stop? So we will again rewrite the pth moment into this form, and we will again see that the asymptotics with respect to t of this integral here only depend on the asymptotics of the determinant. So in order to study the asymptotics of the integral, we will study the asymptotics of the determinant. But what are the asymptotics of the determinant? Yeah, well, how can we study the asymptotics of the determinant? This we can study by the well-known notion of Lyapunov exponents. And for this reason, I will define the following quantity. So the quantity for the limit t approaching infinity of the natural logarithm of the determinant of dx ut divided by t being equal, if this limit exists, obviously, to some lambda depending on u and depending on omega, maybe, almost surely, then this notion, if existent, is called Lyapunov exponent of this random field here, the determinant. Okay. And why is it helpful? So let's assume that P0 has compact support. Actually, that assumption we will not drop. And lambda is smooth enough. We don't need this assumption, but it can also be restricted. Well, we don't need this assumption in the main result, but it can also be restricted anyways. And one has approximately that the determinant of xut for big T approximately behaves like the exponent of lambda of u times t. Okay, so what then we get? We get then that the limit for t to infinity of our investigated quantity, so the integral of p0 of u to the power p times 1 over the determinant to the power p minus 1, is approximately equal to the limit t approaching to infinity of, well, this rewritten to exponent of minus lambda u times p minus 1 times t. And now by some well-known result, for example, the Laplace method, if lambda is smooth enough, we get that this limit can be computed as the supremum of u in the support p0 minus lambda u times p minus 1, almost surely. There are even newer results. I guess Laplace's method is from the 19th century or something, but there are rather new results which don't need such smoothness, which can also be applied to compute the logarithmic asymptotics of this Laplace transform. But I will not emphasize on that anymore. And after we computed this, we can see that oh, this is actually a mistake. I'm sorry that this here divided by p is strictly increasing if and only if this here is greater than 0. Yeah, so this is this can easily be computed. So if we can work with our Lyapunov exponents properly, then we can get our desired result. Therefore, we want to make these approximations rigorous and impose conditions such that the Lyapunov exponents are negative. And for this, we have the following theorem. Let a of u mu be equal to such an integral kernel of phi of u minus v mu dv with the property with the following dissipativity condition. So the scalar product of u minus v, in scalar product with phi of u minus phi of v should be less or equal than minus alpha times the difference of u and v squared for some alpha greater than 0 and all u and v in Rd. And furthermore, alpha should be chosen such that alpha minus b squared over 2 is strictly greater than 0, where b squared is actually the Lipschitz constant of beta squared. So, well, b is the Lipschitz constant of beta, not b squared. Then the intermittency phenomenon occurs if we have an initial measure with compact support. Yeah, sorry for that. So this is another assumption. We need compact support of our initial measure in order for it to occur. Okay, so what do we get from the imposed dissipativity condition? So it is chosen like that. So our two trajectories will always try to go together with an exponential rate. And in this way, we get somehow for the distribution of for the mass distribution of our stochastic flow, we get a concentration of mass in a sense. But more mathematically, the imposed condition imply for gamma being equal to 2 times alpha minus b squared, which is greater than 0, that the differences of two trajectories in square can be exponentially controlled by a positive martingale. And since positive martingales have a limit, the squared distance must converge to 0. So what does that mean? We just apply the Ito formula to this distance in square. Then we get our quadratic variation term and the normal martingale term with a scalar product though. And then by the imposed conditions, we can estimate this with the difference of u and v in square minus 2 times alpha minus b squared times the integral from 0 to t of our differences again, and then plus some martingale part, which is the scalar product. Okay, then from this, we can, by applying Ito's formula again to the exponent times exponent of gamma times t times the difference squared, we can estimate this by some martingale yt of uv, and it is positive because these quantities are positive. Actually, one can directly see what this martingale has to look like. It is exactly this, but times the exponent of gamma s. So you integrate this times exponent gamma s. And then the lim sup of this here must exist because positive martingales have a limit. And if the lim sup of this here exists, the two trajectories must go to 0 almost surely with an exponential speed, actually. Okay, so what can we gain from this in our concrete problem? In order to tackle our problem, we want to first rewrite the Lyapunov exponent, or well, the quantity logarithm of the determinant over t into two parts. It is the bounded variation part. Well, here should be a t divided by t, plus a martingale part divided by t. And we will denote them by ft of u plus gt of u. And we will show that this quantity has a limit which is uniform on compacts. And this is crucial in order to obtain the main result. So in order to prove that, I will show 3 lemmas which give this result in the end. So the first lemma is uniform convergence of the martingale part. And this would be under the assumptions of the main result. We have that this limit here of the expectation of the supremum on u in compact on Rd of gtu to the power p is equal to 0. So the martingale part, well, the supremum of the martingale part converges to 0 in LP. for all compacts k in Rd and p greater or equal than 1. The idea of the proof is the following. One can get from Kolmogorov's continuity criterion or Kolmogorov-Chentsov or Kolmogorov-Tutoki theorem, however one calls it. We get first, we can derive that our quantity gt is locally Hölder continuous. And thus we have, for the difference of GTU minus GTV, we have that it is less or equal than some random variable times the norm of u minus v to the beta. And then we show that this random variable is actually an expectation. Well, the pth moment of this random variable is less or equal than 1 over t to the p over 2 and times some positive constant d. So for t to infinity, this goes to 0. And this is only possible due to the imposed conditions. Yes. This is only possible because of the imposed conditions. So usually one would have that here one gets 1 over t to the p by the 1 over t, and the integral here should evolve like well, square root t plus the, well, times how fast this evolves. But this doesn't evolve very fast because the trajectories here converge to each other. So we only have a behavior asymptotically of order square root t for this martingale. Okay, then the second part would be an Arcela-Ascoli result for the bounded variation part. And let me, for that matter, recall the Arcela-Ascoli theorem, which we used in this context. And for this, let K be compact set of Rd, and Fi be some collection of continuous functions on K. Then Fii is pre-compact if and only if there exists some constant such that it is uniformly Lipschitz or uniformly Hölder, but we will actually have uniform Lipschitzness. And at every point, or in the case of uniform Lipschitzness, only at the point 0, for example. Oh, well. Yeah.
I think that it is not necessary to say that if and only if, because the general Ascoli-Arcela theorem says us that we need only uniform condition of uniform continuity. Yes,
yes, yes. The boundedness is not necessary.
This is if
Lipschitz conditions.
We don't have to say that if and only if, just if there exists C such that. Yeah.
Yes. Okay. Thank you. Yes. Well, when we have uniform boundedness at some point. Okay. The lemma says that under the assumptions of the main result, we have that Ft, well, the bounded variation part is almost surely pre-compact in Ck for all compact K in Rd. So what is the idea of the proof for that result? The main problem here, the main problem here is the uniform Lipschitz property, and the boundedness property follows from the boundedness of the coefficients. So the uniform Lipschitz property we obtain as follows. So first of all, we can estimate by, well, Lipschitz properties of the coefficients that FTU minus FTV is less or equal than some Lipschitz constant here, which I unfortunately forgot, times the integral from 0 to t of the differences of our two trajectories. And this all divided by t for all u and v and k. And then we proceed by showing with Grünwald's lemma that actually our differences of the trajectories in norm squared are less or equal than u minus v in norm squared times times this large expression here.
Alexander, could you please recall us what is FTU?
Yes, sure. We have decomposed the logarithm of the determinant divided by t. If you remember, the determinant was an exponential.
Yes.
And well, it was an exponential. Well, let me recall it. So it was this exponential. And then, yeah, we have these coefficients here, and FTU now is just the integral of these coefficients with which I have denoted by fx of us mu s ds. This here is just FTU, and this is a typo. This should be a t.
Okay, thanks.
Okay, and the martingale part is GTU. Okay, so the coefficients which are, well, hidden in FTU and in FTV are actually Lipschitz, so we get this estimate here. And then with Grünwald's lemma, we get this estimate, which is what we want, the difference of u minus v and square.
And
yes.
Do you apply Grünwald lemma to equation for x?
Sorry, no, I apply the Grünwald lemma for this here, for the difference.
But this difference has a stochastic part.
Yes, and this is here. So let me recall it. So we have this here, right? This is the stochastic part. This is what you're talking about. So I just apply the supremum, and then it is.
You just take supremum of this stochastic integral.
Exactly, exactly, exactly. Yeah. Thank you for asking the question. This is actually, yeah. This is actually a good point. So this is where this supremum here comes from. And not only do we need this supremum in order to...
I'm sorry, maybe I missed something. Shouldn't be then it be a sum with the first factor u minus v squared?
Sorry?
I mean, after the application on the Grünwald lemma, shouldn't we get the sum of this u minus v squared and this stochastic integral?
Yes, here we get this. So this
is... so the first term u minus v squared and the last term, which is this stochastic integral, they should go...
Alexander replaced this stochastic integral by a constant.
Sorry?
So I still do not see, if honestly.
By a constant? No, I just replaced this. Yeah, I replaced it by a random. By
a maximum value at point t.
Yes.
Yes, exactly. But then it should be exponent to the power 2 alpha minus b squared t times the sum u minus v squared plus the maximum of the stochastic integral. Shouldn't it?
That's true.
And this here you have multiplication.
This is true. Yes. This should be a sum.
This may not matter for further application.
Actually, this is a good point. Actually, I missed that. So this should be a sum. But okay, then thank you very much for the comment.
You're welcome.
This is a mistake I missed, but it doesn't matter in the result, gladly.
Yeah, it's
because because we actually show that this here, this quantity times the, well, we get this here this times this. Well, I write it down here. Okay, sorry for the confusion. So we define this by xt, and well, in general, well, before it was actually supposed to be that it is just finite, almost surely. This should suffice, but it doesn't suffice because you did see a mistake here. But what we actually have is that the limit of this is 0. So yeah.
So probably you don't have equicontinuity from this estimate. You have only you have some bounds for large t.
Why? Because he said that it is less than this u minus v. Okay, let us
plus a constant,
plus
constant.
1 plus constant. This does not matter.
But it does not converge to 0 if u converges to v. This inequality does not imply even continuity.
For fixed t, for fixed t.
For fixed t.
Yes, but okay. For fixed t, yes, but in the limit we have it.
But then how the result is written? Because for fixed t, it's not the precompact set anymore. It's like it should be reformulated maybe slightly.
Yes, well, sorry, where was I? Yes, so first of all, it should be reformulated, and then, well, the main thing is that we want to get a converging subsequence. And yeah, okay, yeah.
So if you start to take the sequence of t, which is rapidly increasing, then you can guarantee that these differences are more or less very close one to other. Yes?
Yes.
It may be done easier. Just apply Kolmogorov-Chentsov theorem for xut minus xvt. And that's all, because it's easy to calculate moments.
It was my first suggestion, but it became to be rather technical. So this way, look at much more easy. But
okay, so
then we have just to discuss this subsequent of t, which rapidly grows to infinity. In order to have this supplement term very small. Then for any epsilon, we can just find such Tn for that for t which is greater than Tn, we will have that this difference is less than u minus v and something plus epsilon. Yeah, so we can prove equicontinuity.
No, we cannot prove even continuity, only for the limit. But
yes, for fixed t, we can, I am not speaking about fixed t. I am just saying that for any epsilon, we can find such delta and such n, that for n greater than this n0, we will have that this difference will be uniformly small, smaller than delta.
Yeah, this is true, probably.
Yeah.
Okay. Yeah, thank you for the comment. I guess I have to be more careful here.
However, you have to prove that this supremum in u and v of stochastic integral is bounded. And
yeah,
how did you proof?
So it is in the same spirit as this here.
Mhm. Okay, I
So
see.
it is
Thanks.
not exactly the same, but it is the same spirit. And actually observe that for u equal, yeah, well, we use actually, well, I use special compacts which include 0, but from that theoretically, well,
Okay,
from
and you use Kolmogorov for stochastic integrals. I see.
exactly, yes,
Mhm.
exactly. And then I see, yeah, and then I can actually, well, I show that this times this converges to 0 for t to infinity. And this one can show in a similar way as, yeah, well, one would prove well, one uses the technique as in the proof for the law of iterated logarithm with the Borel-Cantelli lemma. Yes. Okay. Yes, thank you very much for the comment. Yeah, I have to be more careful here. But let me continue. So the last lemma, alleged lemma, would be the following. So under the assumptions of the main result, there exists lambda strictly less than 0, such that for all u in Rd, this limit here is defined. It is independent of u. And yes, it's negative. So I only have a sketch of the proof why it is well defined, because this is the more critical, yeah, the harder proof. And here this is actually the only place where well, in my opinion, I actually need the special form of the diffusion coefficient, because one can see that this limit here exists because we can pull the limit in, and we know that xut converges to xvt, and well, then the limit just exists and is equal to these coefficients being equal to 0. And to prove that it is negative is actually the easier part. So the, well, here I have a mistake, but everything would work with more generic assumptions, but here we do actually need this concrete form. Okay. Then the proof of the main result would be the following. Well, with a simple subsequence argument where I have to be more careful, one would be able to identify a limit lambda such that the supremum of all u in the support of P0 and well, the absolute value of this quantity here converges to 0 almost surely. So we have convergence on the compact that we need. And hence, for all epsilon greater than 0 and u in the support, there exists a t which is independent of u, because this should be uniform on the compacts, such that this here holds. Yeah, this just follows from this.
Do you suppose that support is a compact?
Yes, exactly. The support is compact, exactly, yes. Yeah. And then we can get the following estimates for the quantity which is being investigated. So from above by some exponent times exponent of minus lambda minus epsilon times t times p minus 1. And here the same with plus epsilon times the integrals by logarithm. Sorry, was there a question? No? Okay. And by logarithm laws, these limits vanish for these guys. And what remains is this here, because the logarithm cancels the exponential and t cancels with the t here, and the same here. And by letting t go to infinity and afterwards epsilon to 0, we get that our quantity gamma p over p is equal to minus lambda times p minus 1 over p. And this is strictly increasing because lambda is less than 0. Lambda is negative and therefore minus lambda is positive. Okay. And yeah, this since lambda is less than 0, it is strictly increasing, and thus this quantity here, gamma p over p, is actually strictly increasing, which is the definition of intermittency. And well, yeah, one goal would be to generalize this result so first of all to get rid of the mistake, but after that happened, maybe to generalize this result to a more general class of diffusion coefficients, because it is only in the step of the existence of the Lyapunov exponents where this is actually needed. Or in my opinion, it is I think that it is only in this step where it is actually needed. Yeah. And this was my talk. And thank you for your attention. And I am now, do you have any questions?
Okay, thank you very much. Maybe somebody have questions or comments, please.
I have a question. Could you please specify a constant lambda?
What do you mean specify?
No, just find. It seems to me it is possible because you know that all particles coalesce.
Yes.
So you have 0. So xu minus xr is close to 0 if t is large.
Yeah. This converges to the divergence of phi of 0 minus 1/2.
Yeah. So this was my question. So
you
know lambda.
Yeah, but it's too big for the slide, so I just called it lambda.
Okay.
Yeah.
Other questions, please?
I have a question. So for the proof of the existence of the Lyapunov exponent, I thought that you use at some point some ergodic theorem or multiplicative ergodic theorem or something like this. You use it or not?
No, I don't use it. So that was actually, I tried that, but it didn't work out. And actually, it works more generally than what I have considered anyways. So one can just directly compute it. So it is not needed, even though, it looks like it would be good to use it.
Other questions, please? Let me also comment. Okay, Andrei, let me continue already.
Okay.
Okay, so I have to say that, of course, the result can be extended, in my opinion, just with some technical difficulties which can be overcome on a case when initial measure has not compact support but has rapidly decreasing tails. This is the first one. Second comment is exactly about the idea of using Lyapunov exponent. The crucial step here is that in our condition of dissipativity, in frame of dissipativity, we have that any two trajectories goes close one to other. And it occurs that in these conditions, we not only can say this, but we can control how fast. And they came close one to other uniformly, roughly saying, with respect to space, with respect to direction in the space, and so on. From this point of view, of course, this dissipativity conditions seems slightly restrictive. But this is the difference between the one-dimensional case and multi-dimensional case. And I want to recall you that in one-dimensional case, Maria Karlikova-Lagunova was able to prove that in stochastic flow, the very very wide condition, like we just have in our case Lyapunov exponent equal to 0. Any two trajectories have a difference which is going to 0. Here we have to control the different directions of the space, so we impose this Lyapunov approach. Of course, the comment about ergodic theorem was very interesting, and it was an attempt to do this, but still we have the interesting difference between the equationless interaction and usual stochastic differential equation, which says us that the Markovian structure here is much more complicated. The process mu t itself is Markovian. So maybe when we just forget about x, ut, and so on, then we can try to apply ergodic approach. But at the moment, we are in stage just to think about this and consider different partial cases and different attempts. So the question is that the Markovian structure is based on the Markovian structure of the process mu t. Okay, so that's what I wanted to emphasize. Andrei, you said that you have some questions.
No, maybe a comment. Sometimes it's easier to prove uniform convergence to 0 if you consider Sobolev theorems. And if you have moments for derivative with respect to u, and if you prove that derivative in LP sense converges to 0, then maybe you'll get uniform convergence for free, and you can and derivative satisfies linear equation. So I think it is, so it can be done like this.
So you mean the embedding
yes,
theorem?
Yeah, Sobolev embedding theorem.
Yeah, exactly.
Okay.
Exactly.
Thank you for the comment.
And it seems to me that you will have a stationary solution if you consider, well, not a flow, but if you subtract the center of mass of a flow, or if you subtract x0t, something like this.
Yes, exactly.
And everything will attract to this center of mass.
So we will have
like shift compactness.
degenerated stationary solution. Yeah?
Yes.
Yeah. Well,
all mass will be concentrated at one point. Yeah.
In a limit, yes.
Yes, but this is stationary case. Yeah.
In a limit, no. So mass will not be a stationary process, but if you center,
if we subtract,
if you subtract the
exact,
center of, then you will get yes.
You paper with Maria Karlikova about the shift compactness. Maybe you remember.
Yes.
So this is exactly the same. Okay, thank you very much. Some other comments, please.
I have one more question, or just I ask everybody. So in Navier-Stokes or stochastic Navier-Stokes, people now are very interested in the opposite regime when the Lyapunov exponent is positive. When they have some version of a chaotic behavior, this is what they call. I mean, do we have any? I mean, of course, this is not under a dissipativity condition, but I mean, is there a situation thinkable where you can prove that even you have just the opposite behavior, like a positive Lyapunov exponent?
I expected that we can have some ergodic behavior in this case exactly as following. As we know, Navier-Stokes can be substituted by Helmholtz's equation for some finite number of infinitesimal vortices. And there are cases when we know for sure that the system of these vortices have some like stationary behavior. So at least for vortices, a number of small numbers like 5, 7, 8, we have after simulation, and it can be proved as far as I remember for number 5 rigorously that we have some stationary cases. Also for Helmholtz equation, we have the two good first integrals. Yeah, and energy and moment. So we have the manifold, and this manifold is closed. So from this point of view, one can expect that we can apply some ergodic theorem in this case. Yeah, at least it will be done for the discrete mass. But we have here this P0, so it can be a good point for future investigation. Thank you. Some other comments,
maybe
please?
one more comment. Maybe it will be useful to apply not Kolmogorov type theorem, but it's called Garcia-Rademich-Ramsey inequality, or maybe Slobodetsky spaces. Well, it is some generalization of Kolmogorov, but you may try, and maybe it would be easier to
What
work
does
with.
it say? Sorry, what
like
is the theorem?
like Kolmogorov, like Kolmogorov, or like Sobolev embedding, but who knows? Maybe it would be easier to consider supremums of XUT in U.
Okay. Thank you.
Okay. Some other comments, please? If there are no any comments, then thank you again for interesting talk. And Georgi, do you know, do we have next speaker?
Yes, the next speaker will be King Song Wang.
Oh, okay. So we'll have a talk. I didn't. I don't
Geometry
remember.
of Gaussian random curves.
Okay, very good. Thanks everybody, and see you next week on our session. Bye.
Thank you.
Bye. Thank you.
Goodbye.